We continue the theme of blending, and today we will look at the space-time blending. This is one of the methods of metamorphosis. Contents of this lecture is following. First of all, we will consider approaches to two-dimensional metamorphosis and general transformation problem. Then 3D blending and proposed approaches of the metamorphosis based on the space-time blending. The space-time blending is based on the bounded blending and function representation. Therefore, we will consider these topics too. This lecture is based on this article. Shape transformation is an important operation in animation and free-form modeling. It includes simple linear transformations such as translation, scaling, and rotation, non-linear transformations such as free-form transformations, and other non-linear space mappings and metamorphosis or morphing, transformation of one given shape into another. Such transformation is similar to the behavior of a biological amoeba illustrated in figures. This lecture is devoted to the method of shape transformation, including non-linear motion and metamorphosis with using implicit surfaces and function representation solids in more general cases. Approaches to 2D metamorphosis are well developed for two given simple polygons. They use physically based methods, star skeleton representation, warping and distance field interpolation, wavelet-based and surface reconstruction methods. A detailed description are available at the corresponding links. These existing approaches are based on one or several of the following assumptions. Its equivalent topology, mainly topological disks or balls are considered, polygonal shape representation, shape alignment, when shapes have common coordinate origin and significantly overlap in most of the case studies, possibility of shape matching, establishment of shape vertex-vertex, control points of other features correspondence. The resulting transformation should be close to the motion of an articulate figure. The specific aspects of the shape transformation problem considered in this lecture and solved by proposed method. General transformation problems are following. First of all, initial shapes can have arbitrary topology not corresponding to each other. Then the shapes can be defined as two-dimensional polygons, implicit surfaces, or constructive solids in two- or three-dimensional space. Next, the shapes are not aligned or overlap and can occupy different positions in space. Also, there is no correspondence established between the boundary points of the shape features, and combined transformation similar to biological amoeba motion. The space-time blending method employs the function representation solids and bounded blending. Let's recall these notions. Function represented models use real-valued functions of point coordinates, function of two variables x and y for two-dimensional shapes, and function of three variables for three-dimensional shapes. The advantages of function representation are following. Function representation solid can have arbitrary topology. Then two-dimensional polygonal shape can be converted automatically to a two-dimensional function represented solid. Also, function represented solid can be constructed using primitives and operations. And there are analytical formulations for set operations and blending. Blending operation generates smooth transition between two surfaces, usually used for modeling fillets and chamfers. Blending union of two disjoint solids with added material is a single solid with a smooth surface. This operation is based on approach to the shape transformation. Blending operation based on R functions uses set theoretic operation with displacement function. You can learn more about the blending operation in the previous lecture. Let us formulate step by step the space-time blending approach and illustrate it with two-dimensional initial shapes. First step, two initial shapes are given on the xy plane, in our case a ring and a cross. Second step, each shape is considered as a cross-section of a half cylinder in 3D space, a cylinder bounded by a plane from one side, as is shown in figure. Step number 3. The axes of both cylinders are parallel to some common straight line in 3D space, for example to the coordinate z-axis, and the bounding planes of two half cylinders are placed at some distance to the given space for making the blend. Step number 4. Apply the blending union operation with added material to the half cylinders. Step number 5. Adjust parameters of the blend such that a satisfactory intermediate 2D shape is obtained in one or several 2D cross-sections by planes orthogonal to the z-axis. Step number 6. Considering an additional z-coordinate as time, make consecutive orthogonal cross-sections along the z-axis and combine them into two-dimensional animation. As shown on this slide in right figure, the initial shapes cannot be obtained even in cross-section with large absolute values of z-coordinates, because the global or unbounded blending is applied. Therefore, to solve this problem, we have to use the bounded blending operation. Let's recall that bounded blending operation uses bounded displacement function that limits the area of influence of blending. A plot of one of the possible expressions of a bounded displacement function is shown in this figure. As we discussed in previous lecture, one of the type bounded blending uses bounding solid as a displacement function. The additional solid is convenient to control the blending operation. Here is an example of bounded blending operation. You can control the place and size of blended area by bounding solid, the third transparent shape on this slide. Applying bounded blending allows to get the initial shapes in cross-sections during shape transformation. Let's look at this as an example. Bounded blending of two half cylinders with a disk and a square as cross-sections and two bounding half spaces is presented on this slide. Here you can see a sequence of animation frames where the disk is transformed into a square using bounded blending. Here you can see this animation. Another example is a ring to a cross transformation. We apply the bounded blending union to obtain smooth transitions between two half cylinders for the shape transformation. The half cylinders are bounded by the planes z equals 0 and z equals 1 to make the gap from 0 to 1 along the z-axis between them. As can be seen from this figure, the blending displacement from the exact union of two half cylinders takes zero value at the boundaries of the bounding solid, planes z equals -10 and z equals 10. This results in the exact initial 2D shapes obtained at the cross-sections outside the bounding solid. Here you can see a sequence of animation frames, ring to cross. Here you can see this animation. Let's consider the application of the proposed approach to the transformation of two polygonal shapes of arbitrary topology. In our example, there are two shapes. The first one is Buddha, the second one is Chinese character. An arbitrary 2D polygon, convex or concave, can be represented by real functions. The Buddha shape consists of the main concave polygon, 49 segments, and two simple polygonal holes. The Chinese character consists of two disjoint components, one of which is a simple concave polygon, left part of the character, and another, right part of the character, is a concave polygonal shape, 12 segment with 5 holes. As one can see, the initial shape have quite different topology. They were placed on the plane without overlapping. Here you can see a sequence of animation frames, transformation of a Buddha shape into a Chinese character. Here you can see this animation. Now let's discuss the 3D case. The space-time blending procedure for initial 3D shapes consists of the following steps analogous of those applied for 2D shapes. First of all, two initial 3D shapes are given in x, y, and z space. Next, each shape is considered as a 3D cross-section of half-cylinder defined in 4D space-time, a cylinder bounded by a plane from one side along the time axis. Next, the bounding planes of two half-cylinders are placed at some distance along the time axis to provide an interval for making the blend. Step number 4. Apply the added material blend operation to the half-cylinders. Step number 5. Adjust parameters of the blend such that satisfactory intermediate 3D shapes are obtained in one or several cross-sections along the time axis. Step number 6. Make consecutive orthogonal cross-sections along the time axis and combine them into a 3D animation. Here is an example of 3D metamorphosis of torus and union of two solid balls. This is more complex example, where 3D letters are transformed to shape a robot. These are frames of this animation. We can improve the user control of space-time blending by using smoothed half-cylinders or add additionally fine and non-linear transformation using feature points. Also, interactive editing and real-time rendering are available by using plugin to Maya software and GPU processing. In practice, sometimes the transformation of one shape into another is too sharp when half-cylinders are not smoothed. Therefore, to make the translation between shapes softer, the smooth half-cylinders can be applied. The application of smoothed half-cylinders gives softer and smoother result. You can see the smoother result on orthogonal slices. We can apply additional deformations. As example, metamorphosis with disjoint components and additional nonlinear mappings. For interactive rendering and editing 3D animation with using space-time blending operation, we have a modeler for Maya software that allows us to export and functionally presented model to different formats. In this case, we just export the function as CUDA code and use NVIDIA compiler to produce the actual code performing evaluation on the GPU. The model can then be rendered in real time in our viewer in game or some other application.